Welcome to today's webinar on TANICS, the automated nuclear irradiated container solution, a high-quality robotic welding and inspection system. The purpose of this webinar is to introduce TANICS and also the problems it has been developed to address. What is the problem that TANICS has been developed for? The UK nuclear market currently has a large amount of nuclear material such as uranium, which needs to be transported off the respective sites for long-term storage at Sellafield. In addition, Sellafield have similar internal requirements for material storage. Similar requirements exist abroad in places such as Fukushima. Transporting nuclear material for long-term storage without the need to repackage at the storage location requires the use of sealed stainless steel 316L containers for long-term corrosion resistance. Container lids are generally welded to the container body for storage, as this provides a robust and metallurgically predictable seal over the lifetime of the storage. However, due to the highly radioactive nature of the material in the containers, all welding and subsequent inspection must be carried out remotely. The containers used are manufactured using austenitic stainless steel, such as 316 and 304L, due to their excellent resistance to corrosion. Pipe material is generally used for the main body, whilst the neck area and lids are machined from bar stock, two forms of the same material which weld differently. The weld configuration to attach the lid to the body is a full penetration butt weld with the acceptance criterion of PD 5500 Category 1 and Sellafield Build Level 1 ES_5319_2 with nil surface breaking defects in the weld, a very demanding acceptance criterion. Due to the high rates of radiation as a result of the fuel material, all container packing and sealing activities must be carried out remotely inside specialist cells on the client's site. Cells have manipulators fitted for operators to handle items, and the windows and concrete walls are circa 5 feet thick, with cameras providing additional viewing capability. Robots and equipment within the cell must be able to survive in the highly radioactive environment. Survivability can be enhanced using shielding for critical items with sensitive electronic equipment positioned outside of the cell. So how could this be done? Introducing TANICS, which has been jointly developed by byJacobs and Langfields to address this problem. TANICS consists of a robotic welding system working with robotic eddy current testing and visual inspection systems to seal the containers. In addition to this, TANICS also provides a modular container design, remote gas purge system, as well as data management for quality control. Robotic welding is not new, and the automotive industry has considerable experience of this. However, welding robots in the automotive industry are performing stitch welds, not closure welds, which are required for containers. A closure weld requires the start and stop of the weld to be merged, which provides additional challenges compared to the automotive welding. The material being welded is stainless steel, requiring a tungsten inert gas welding process, unlike the mild steel processes used for car manufacture. The acceptance criteria required by the nuclear industry is very demanding. The robot must also be capable of performing high-quality, repeatable welds without intervention. In the video, it can be seen that the upper portion of the test piece, representing the container, protrudes through the cell floor, requiring a 2G position weld. This is a common arrangement in cell, although horizontal 1G position is also possible. To carry out a full penetration butt weld, the internal container atmosphere must be free of oxygen to prevent oxidation of the weld root. This is normally achieved by purging using an inert gas which enters via one end of the container before leaving at the opposite end, as is done with pipe welding. However, storage containers only have a single point of entry, which does not allow for a standard purging process. To address this problem, Tannix incorporates a vacuum and purge system to remove oxygen from inside the container before purging with an inert gas, such as argon or helium. This inert purge remains in operation throughout the initial root weld. It is not required thereafter. Post-welding, the container will need to be inspected remotely to ensure the acceptance criterion have been met. The separate Tannix inspection robot is fitted with cameras and an eddy current inspection system. The cameras provide footage of the entire weld from two different angles to allow the weld profile to be assessed. The visual system excludes ambient light and provides its own internal lighting to reduce shadowing and mitigate the effect of sodium lighting. The eddy current system also inspects the entire weld and displays it on screens. The eddy current output is displayed on monitors concurrently with the visual output. The Tannix robot welding system has completed a number of test welds, and the approval of the weld procedure qualification record is currently in progress with an independent third-party body. The Tannix eddy current robot is undergoing integration with the welding robot under a single software control system. The system is currently being set up at Jacobs Birchwood Laboratories to undertake client demonstrations for specific project work. Tannix has the capability to weld and inspect a range of container diameters, resulting in a series of modular container designs that are compatible with this system. Tannix can also be operated remotely, allowing inspectors to assess the weld off-site, reducing travel costs using a secure remote connection. This webinar has introduced Tannix and its capabilities, which have been designed to address a particular problem in the nuclear industry in the UK and abroad. There will now be a question and answer session. Feel free to ask any questions you may have.
Okay, so thank you for bearing with us through our technical issues there. But we got to see the video there in the end. So I'd like to first of all mention that this is actually a joint presentation with the Welding Institution of the North Scottish branch. We've actually got a lot of those members along, so hopefully a lot of questions from them. So I've got a couple of questions here. Our speakers, can you hear me, gentlemen?
Yeah, can hear you. Yeah.
Excellent, we can hear you fine. Okay, so the first question is, what's the qualification for it to harmonise any code standards? How is this qualified against any harmonised code standards?
Essentially, we're aiming at the UK market at the moment. So the design code, we're aiming at PD 5500 with a well-proceeded qualification to BSEN 15614-1. And at the moment, I think the harmonised standard is 2017 version. 2019 has not been harmonised yet. So that's what we're aiming at essentially. We're also, the PQR, which we're doing at present, as past radiography and is at the moment going through mechanicals. We're dual certifying it to ASME as well. So that opens up other markets in the future.
Yeah, I think it also allows people looking at container verification who will use ASME material standards for validation. It allows them to sort of link the welding to what they're using for the container validation as well, using the ASME9.
Okay, that's great. We've got an interesting question here. What was the most interesting technical challenge that had to be overcome in the development of Tannix?
Well, I think a couple. Number one, neither of us are robot people, which I think probably ended up being a little bit of a benefit, because rather than essentially robot people trying to weld, this is welders welding, and then we get robot people to sort of make it do this, make it do that. But we still need to understand what the capabilities of robots are, and we're new to that. So that's one.
One of the other things that is of primary concern for us is the various levels of radiation and what effect that will have on the robots.
Yeah.
What we've been looking at is we essentially plan to have 2 robots for the system. They'll be in lead-lined boxes essentially, and the roof will retract, and the welding robot will come out and actually carry out its welding functions, then back into the lead-lined box, and the eddy current robot will come out and carry out the eddy current. What we've got to do is to minimise the exposure of the robots to high levels of radiation. But the figures that have been checked so far, we think we're fairly comfortable that it'll work.
Yeah, I mean, in a fuel cell, when fuel's out, could be in the region of 30 sieverts per hour, which is lethal to a human, and not great for electronics. The majority, pretty much of all the sort of sensitive electronics are outside the cell where the humans are, and what's inside the cell is the robot and the sort of the business end of the welding equipment, which is mainly electrical motors and the like. But there are encoders, positional encoders on the robots, which we need to look after. Now, when the fuel is packed in a container, and some of the sites, the container will come through a floor or come through a wall. The flooring in the wall provides a large amount of shielding, but then we end up with a collimated dose coming out through the lid, which we just need to be wary of with the robots. And as Wayne said, by keeping them, when they're not in use, keeping them stored away in boxes, that just adds to the longevity and just protects them from radiation dose that they don't need to be exposed to. But that's one of them. And yeah, just the trying to get the robot to do the things that a human would do in a closure weld. That's another challenge.
Yeah, we've had, one of the issues has always been closing up of a joint. Essentially, the joint that we're using means that we have to close up full thickness material, and the challenge there is, because of the high amperage that we're using, we've got to actually get full fusion and solidification, and it needs to actually close down so we don't have any defects in the root.
Yeah, that makes an awful lot of sense actually. Achieving that is quite difficult. Normally you would do that sort of thing with a number of passes. Okay. Okay, so we've got another question here, and this is to do with training, certification and experience. What are the requirements for that, for the eddy current operators?
So the eddy current system will be, I'm not an eddy current expert, but it'll the training will be as per the usual sort of PCN levels.
The procedures will be written by PCN level 3s. We will be using PCN level 2 operatives to carry out the work. What we will be doing, the plan is that we will do extensive training at the moment in the Birchwood facility to familiarise ourselves with the work that we're doing. The good thing is that because the way we're setting it up, we did a previous project for a nuclear facility where we actually did on-site radiography, and then remotely, hundreds of miles away, we were emailing the radiographs, and the radiographs were being interpreted at different parts of the country. So what we're looking at doing is, because this is going to be on video cameras, we can actually see the weld, we can actually see the eddy current, but obviously the people are not in the room. They can't be because of the level of dosing. So effectively they've got to be outside the room. You could have the machine welding in London and the inspector could be, say, in Glasgow, for an example.
Yeah, absolutely.
Okay, the wonders of technology, yeah. And this is a question, someone actually asked this question, and I'm thinking to myself, the separate port that's used for gas purging, how is that actually sealed itself?
So there's one valve into the container that's normally a self-sealing style sort of hydraulic coupling, something along the lines of a Hansen style coupling, and that's the only method of getting gas in and out of the container. Reason for that being, obviously with a normal sort of purge arrangement on such as a pipe in one end out the other, if, as I said earlier, the container's coming through a floor or coming through a wall, then that container essentially breaches two containments. Now, if the back end of that container is already welded up and sealed and leak tested in manufacture, then as long as the seal around the container coming into the welding area is okay, then there's no containment breach. But if we were to put a valve in the base and try and treat it as almost like a standard pipe purge arrangement in one end out the other, we would have to connect to the base and then bring a hose or a pipe back into the cell. And that would cause probably the safety people an awful lot of worries in how you prevent what happens if the hose leaks, what happens even with a self-sealing coupling and detaching, what if momentarily there's an exposure of the insides of that container to the second containment. So hence why going in one end is virtually in concrete. We can't change that. So that pushes us down the line of a more elaborate purge system to try and keep that oxygen level to the required minimum.
Okay. So we've got a question here about validation. Are there any requirements to validate the eddy current system?
Yes. Yeah. So currently, what we have a number of welded test pieces, and they have defects machined into them. And what we have is a series of test pieces that start with large defects and get ever smaller. So the largest ones you can see with the naked eye, and they're in known positions on the weld. They're normally machined in using EDM, so we get a nice accurate machine. Normally one on the toe, one at the crown of the weld in a different position, and then one transversely across it as well. And then once they've validated to those known defects, then they'll get smaller, smaller, and smaller, and that's essentially how it's done.
Okay, very good. Okay, we've got a question about weld repairs here. In the event of any weld repair, how could that be managed?
What we're thinking there is we're working to essentially let's pretend it's a UK manufacturing facility, so we're going to be working to 5391_2. So the guidelines we have to meet are within the criteria of that specification. If we had an issue with a weld, it would have to be subject to the levels of acceptance criteria within the spec. If we're outside that, a decision would have to be made at the time. The issue could be that we're actually going to cut off the caps. Our experience tells us at the moment that the radiography, we've got to a level now where the radiography that we're actually doing, the welds are blemish free. We're not even getting a pore in the welds. When we started off, we were getting shrinkage craters. So we've done quite a bit of trial work now where we've closed up the shrinkage crater. We've got the optimum parameters that are allowing us to get a full penetration weld where the root is closing perfectly. And we know that the radiography that we're doing to PD 5500 and category 1 and to the requirements of 5391_2 build level 1. Mm-hmm. We know that the results we're getting at the moment are acceptable. So we're fairly confident that if we can get all the canisters machined within the tolerances that we're going to set for the design of the manufacturing joint that we're going to do, i.e. OD of the pipe, wall thickness, We'll be checking the chemistry of the materials that we're going to use. We'll be controlling the chemistry. So we know that essentially once we've done the weld, we're essentially bookending so that we know we should be able to get repeatable results. We've got a history of doing a project between Jacobs and Langfields and various other partners where we've delivered a number of canisters to the nuclear industry that were blemish free. So we've got a bit of history there.
Yeah, I think it's fair to say that we're confident that we wouldn't suffer any failures, which sounds a bit big-headed, but we haven't really in the past. But if we do suffer a failure, particularly in the root, then it would just be start again, repack and start again. Not in a position to get into a cell and start repairing, particularly in the root.
No, I wouldn't think you want to get into the cell.
No.
Okay, so this is someone from the nuclear industry has actually asked this question, and I think they know more than I do. But I'll ask the question. This assumes that the waste canister is cylindrical. If the geometry is cubical, what are the technical challenges, particularly around corners?
One of the things that we've got with the system we're using at the moment is because we're welding a cylinder and the robot is obviously is moving round the circumference of the joint, we can set it at the moment, say at 0 degrees and 90 degrees. And if we put the welding, the tungsten, against the outside at 0 degrees, against the outside at 90, then we know the robot's going to travel round through the correct orientation and it's going to stand off at what we set it. The key is if you've got corners, then what we'd look at doing, one of the things we're actually developing with our partner from the welding system is we're looking at putting an AVC on the welding system, and that would allow us that although we've got a set speed of rotation, what it would do, even when we went along and we turn around the corner, the actual tungsten and the head would pull off, so we would maintain the actual distance away from the workpiece as we travel around the corner. So realistically, I don't see an issue with that.
Okay, fair enough. So another question here. Does this system require a bespoke eddy current transducer to work in the high temperature, or does it have a cooling off period prior to inspection?
There will be a cool off period. I mean, our experience of doing these canisters is it cools pretty quickly. I mean, there will be a cool off period in terms of by the time that robot's completed and stowed away and the next one's come out, you've had a period of cooling regardless. And we can even we can modify that some more if we really wanted to, because this isn't a process that's particularly hurried. It doesn't. The sensor isn't necessarily temperature rated, if you know what I mean. It's not seeing that at the moment. It is. It does have a degree of radiation tolerance in it, though. So, and that's arguably the higher risk to the sensor than temperature.
Okay, I've got a question here, but I think it may actually get a wee bit close to your patent stuff, so you can answer this one if you want to, okay? So, what is the required ppm on the back purge, and what is the predicted flow to achieve the required ppm on that purge?
We're aiming for ideally less than 10 parts per million.
Okay.
It depends, the flow rate depends on the size of the canister, so you can't really say it's any specific flow rate.
You've got to, you've also got to be careful what's in it. So the kind of material that can go in there can range from individual canisters carrying loose pins, or larger loose pins, or a fuel subassembly. So obviously that's going to affect the volume and flow characteristics within the container, because with the prep being so close, with it being in the lid, below that we've got best part of sort of 2 or 3 meters worth of just tube, and the gas can potentially do a quick shortcut and take the route out through the weld area, and that leaves the underside and the cylinder untouched. So it does take a while to actually get down to that level. But the other thing we've really been really careful of is when we're sealing up with that root weld, whatever flow and pressure there is in that container will start to rise as we seal up the weld and remove the exits, if you like. And we need to be very careful that that pressure doesn't increase to the point that as we finish off that seal of the root weld, it pops out. So there's an awful lot of work gone into how that flow and the resulting pressure in there is managed so we don't get that. And the other thing we need to be careful of is affecting the root profile in its molten state. If there's too much pressure in there, then it'll start to push on that root, and we could end up with failures because the profile of the root's been affected by the pressure of the gas. So it's not straightforward.
I think something else to add to it is that on the previous project for a nuclear facility, we encountered this type of problem, and we engineered a solution that allowed us to get the pressure right and reduce the pressure as we were welding, so we could close up the weld. And we did a lot of trials to make sure we could do that. So we've got people working at the moment so we can do all that using solenoids, etc.
Exactly, yeah.
So it's something we've thought of, and we do have a fix for the pressure and the flow rate on the backside.
Okay. There was another question here on the back purge as well, actually, and that was if the ppm goes above that, the requirement, does the system stop or does it continue, or what's your sort of?
No, so they're separate systems at the moment. So there's a decision to be made at what point are we happy to proceed, and that's that basically. We have experienced in the past that if it isn't purged properly, you can have oxygen almost waiting at the bottom of that container, because as soon as that arc strikes, the heat's there, it'll just attract oxygen. So success on site is built on lots and lots of trials in labs, understanding what the trend is.
Yeah. Okay, and then of course here's the disruptor question. Have you considered press fitting the base to the tube with no welding required, and possibly a secondary crimp or squidge? So, would a mechanical mechanism do the job? Is the question.
No, not currently. So the acceptance criteria for a packed container is to achieve a certain degree of leak tightness, and that is dictated in, I think it's ISO 12807, which is somewhere in the order of 10 to the -6 pascals per meters cubed. It's as good as airtight as you're likely to see, and you would need to prove that with any mechanical fitting, and prove that it would maintain that over the storage lifetime, which could be up to, for the initial storage period, up to 100 years. Welding is popular because metallurgically, as we said in the presentation, it's well understood. You can predict what it's going to be like as long as corrosion is addressed. As long as it doesn't corrode, then there's no reason to suspect that it won't leak. So that's why welding is popular, and that's what any mechanical seal would have to demonstrate, and that's not straightforward.
So I've got one final question for you, and that is there any other applications for this technology, such as other hazardous materials? You know, I was watching a program on TV about anthrax, and I'm sort of thinking there must be other uses for this sort of technology for some reason.
In terms of pure welding, or the use of just robots?
Just containing things within a, safe area.
Yeah, I mean, it comes down to what your storage criteria is. As I just said there with the previous question, for nuclear storage, it tends to be this leak tightness. They want it absolutely bottomed up. If for other hazardous environments, it can be something that's slightly lesser and still get a decent seal, then it might be that, say, the crimped method that was the previous question asked, that could potentially be a solution there. Or with welding, we're doing, as Wayne said, full penetration butt welds, because this potentially can see pressure if there's off-gassing over the storage lifetime. So we have to use a code compliant weld. But if you've got waste that isn't seeing those kinds of pressures, then a partial pen, screw-on lid, partial pen seal weld, possibly only 1 times round, that kind of thing.
Yeah.
Maybe a lesser acceptance criteria. It's all driven by whatever your storage criteria is in order to maintain safety.
Yeah, that makes a lot of sense. Okay, well, gentlemen, thank you very much for answering all those questions. I think we all learned a lot there. So, Martin, Wayne, that's been great. I think we've got a final slide which we could get on here, which is a thank you slide, and it also gives the details of, am I doing it? Oh, here it's doing it. It's coming up to a slide which says thank you. And there it is. Oh, it's disappeared. A bit of technical issues today. And it gives details of how to claim your CPD. There it is. So if you like a CPD certificate, if you could email nurat.islam@member.imeche.org, you can request a certificate if you need that from your institution. Other than that, I'd like to thank you for joining us today, and I think it's been a great presentation. I've certainly learned a lot. Thank you, gentlemen.
Thank you.
Thank you.